Thanks, guys. Glad to be here. Glad so many made their way here, even if it's not in the center of Munich. But also thanks to TNG for hosting this event. I think it has been awesome already with beers and pizza and nice talks. Okay, so who am I? I am working for TypeSafe. We are the company behind Scala and Akka and Play, and recently behind Conductor, so our commercial offering. I'd be glad to talk to you about these things later. I'm an engineer there, and I have been using Scala for about 7 years and Akka for a couple of years. So today, I'd like to talk about some specific aspects of Akka. But before we get started, I'd like to ask you about Scala and Akka. How much Scala do you know? Who has never written a single line of Scala code? Okay, not so many. Okay, for those of you, just look at it like, I don't know, JavaScript or Java without semicolons. That might help, or not. What about Akka? Who has no idea what that is? Oh, that's awesome. Only one or two. No idea. No idea. Who has no idea what Akka is? Okay, who is using Akka in production? Oh, wow. Couple. That's great. That's great. All right. All right. So I think that's pretty fine. I will show you a couple of slides and much more live coding, live demos and live coding. Please don't throw your tomatoes or anything if it doesn't work. But you can, of course, tweet about it. All right, let's get started. So the topic is reactive apps. So let's define what reactive is. Most of you probably have already heard about or even read the Reactive Manifesto, right? So if not, check it out. It's just a small web page. You can read it in, I would say, 5 minutes. And it defines a terminology for, let's say, typical modern applications. And in my language, reactive is all about being responsive. Responsive is really what matters because it's the cornerstone of usability, right? Your application has to respond in a timely manner whenever possible, okay? That's really important for the users of an application. And to enable responsiveness, we have two other traits like elastic and resilient. Elastic means stay responsive under varying workloads. That means scaling up or scaling out, but also scaling down if there's not that much load on your system. Because you don't want to waste your resources, right? You don't want to pay Amazon too much money if not necessary. Resilient is really interesting, and it has been sort of new for me. Like in my Java EE career, never thought about that. So resilient really means staying responsive under failure. And that's a really hard problem. So you need to employ concepts like replication, like delegation, and stuff like that. There are various ways to do that, and of course there's an Akka way to do it, and we'll take a look later. And at the bottom there's message-driven, which is like the enabler for all the other traits. Because if you have asynchronous messaging, you can build an elastic or build a resilient system. Because asynchronous messaging allows for the receiver to be unavailable. It allows for delegation of failure and all these things. By the way, if you have questions, fire them at me anytime, right? So, the question is, how can we go reactive with Akka and AngularJS? Let me briefly introduce those. So Akka is essentially actors for Java and Scala. Actors are nothing new. They have been invented in the 70s by Carl Hewitt and have been implemented very like successfully in the Erlang programming language and OTP platform. You know about that, right? Akka is really reactive all through. There's nothing which is not message-driven. There's nothing that is not blocking. It's super resilient because in the actor model, you have a way to deal with failure, which is called supervision. And in Akka, it's implemented as parental supervision. So each actor has a parent. And if your actor fails for whatever reason, it's not the job of somebody like the caller to fix that, but it's the parent who has to deal with that. It's open source, and you will see a lot of Akka code, I can promise you. AngularJS is like the second framework or library we are using here. So Akka is called a library, right? Toolkit, library, it's not a framework. AngularJS I would call a framework, HTML and JavaScript framework. Yeah, it's one of those cool JS frameworks for browser-based single-page apps. Christoph already mentioned React. Maybe, yeah, we could switch out Angular and switch in React. Shouldn't be a big deal here. It's also open source, and they call it HTML enhanced for web apps. You'll also see a little bit of AngularJS. Okay, so how are you going to see that? I'll have a demo for you guys. It's called Reactive Flows. There has to be reactive in the name, right? As you can guess from that screenshot, it is a chat application. The famous chat application. So here you have your chat rooms, which are called flows. Okay, as you can see here, there are two flows. And here are the messages, and here's a way to send messages to the current flow. Not too hard to understand, hopefully. So in the following hour, or maybe 45 minutes, I will first build that system as a single node, single server, so to say, application. And then we're going to make it more reactive, resilient, scalable. So the main components or technologies used here are AngularJS for the front end, of course. And then on the server, we have Akka HTTP and a couple of other Akka abstractions or libraries like data replication, cluster sharding, and persistence. And the communication between the front end and the servers is via HTTP, either normal REST calls, normal as opposed to SSE, which is server sent events. I'll explain those in a couple of minutes. But first, let me give you a demo. And for that, I gotta get rid of that. Okay, wow. What's that? Anyway. What I'm going to do is I will, in my SBT session, which you can see here. Who knows SBT? Scala build tool? Okay, cool. So, yeah, essentially it's like an interactive build tool where you can execute your commands or tasks. And it does a lot of nice things. So here I have started a node, a single node, and I will just call it. As you can see here, wow, no flows. So let's add some flows. Unfortunately, there's no UI for that, but hey, who needs UIs? So what I'm going to do here is I will use curl to connect via HTTP, and I'm adding a first flow labeled Akka, and here's a second flow, AngularJS. Okay, I'm just connecting to the local so loopback address and this port and the flows path. And now, we can see two flows here. So they have been pushed from the server to the browser using server-sent events. And I'll explain those in a couple of minutes. So what you can also do now is here say hello Akka, not hell, hello. And it's there, and you can switch the current flow. Hooray. Okay, doke. So what about second browser here? It should, of course, see the same stuff. So yeah, it seems to work. First demo worked. Great. But now let's go back. I will stop that, move back to the very beginnings. And play again. So let's quickly talk about AngularJS. So in AngularJS, you have a couple of main components. One is the templates. Templates are just HTML with expressions mixed in, and so-called directives mixed in. So here you have a div, and here's a directive which tells you, okay, oops, sorry, you want to iterate some array which is called messages, and extract each message or iterate over each message. And then there is something called a filter, so you want to order that iteration by the date property, and this true just says reverse the order, so descending, not ascending. And then within that iteration, you have divs that just extract from that message, it's the iteration variable, the date and the text. Okay? So that's obviously used to print these things here, date and text. Right? All right, that's the templates. Not a big deal, and that's what I really like about AngularJS. It's super simple, it's HTML, and you just need to know a couple of those directives, and you're ready to go. Now, you also need controllers. They are written in JavaScript, or you can use CoffeeScript or anything, but the controllers also hold the view model, right? So they have a view model, which is here, oops, sorry, damn, referenced by this $scope variable. And yeah, you can do all fancy things with that. So in this case here, we define the messages variable in the scope and initialize it hard-codedly to some dummy output, as you can see here, text1 and some date, right? And going back here, you can see the link messages is extracted from the scope, which is defined here. Let's do a quick demo. No slides, but live code. I think I gotta go back. Oh, I already did that here. That's great. So, where's my IntelliJ? Here we are. So, here's the real code. As you can see here, it's essentially the same. And the great thing about AngularJS is that it's completely browser-based. So what you can do is you just open up your browser, look at the page, and know whether it's good or not. So let's do an open source. I'm in the wrong project. Okay, open source name, resources, web. It's a long path, index. All right. So here, that's just the static HTML template with the dummy data. Okay. So it just works. Of course, there's missing implementation here, missing implementation here. But anyway, you can already look at your page, and if you're a great designer, you can make it nice. So controllers.js here defines a couple of things like the dummy flows, the dummy messages, all that stuff. It's pretty easy to mock that up. But we don't want to mock it up. We want to move forward, all right? So let's now go to the next stage and implement just a skeleton HTTP service using Akka HTTP. And Akka HTTP is a very new library. It's still in experimental mode. Has been added to Akka just recently. And essentially, who knows Spray? Has ever heard about the Spray library? Okay, cool, yeah. Essentially, it's Spray, the next version of Spray. So Spray will no longer be developed. but it has been like morphed into Akka HTTP. So what you have to do to write a HTTP server is just a few simple things. First, you need to call the bind and handle method on some fancy HTTP interface and pass a route. I will show you what that means. And the interface and port, like localhost or whatever interface you want to bind to and port. Okay, the route is more interesting. So this route here defines assets and shutdown. These are subroutes which get composed by this tilde. Okay, so assets is just this directive. Oh my God, get from resource directory web. So what that means is whenever you have a path, like in our case /index.html, it will go to the resource directory, which is identified by the name web, and look for index.html. And by accident, if you look here, web, index.html, hooray, here it is. So this is a great directive for static content. If you want to have some dynamic content, like in this case, shut down your system again, you go for the root path. Here's a path matcher. That's a simple path. You could have a more involved path and extract something like an ID or whatever you want to do. Then you have the HTTP verb or the method, like get, post, delete in this case. And then we complete this request. So in this case, we complete delete request to the root path by sending the shutdown message to the HTTP service. And that's a route. That's all you need. A route is essentially a way to handle requests and produce responses.
Sorry.
Yep.
So is delete like the HTTP verb?
Yes, that's the HTTP verb, yeah. There's also get and post and all the verbs. 1.0 and 1.1. And 2.0 is in the works.
Okay. Thanks.
You're welcome. Okay, so let me show you how that looks like. So here we have our Reactive Flows app. Let me close these. These are no longer interesting. That's the main entry point for the application. There's nothing really interesting apart from creating an actor system, which you need for any Akka application, right? And then you create the root actor for this actor system. That's called Reactive Flows. All right, so let's look at this guy. Reactive Flows is an actor which more or less just creates the HTTP service actor. Okay, create HTTP service is here. It's also context actor of, the factory for creating actors. Creates a HTTP service, and the rest is more about supervision. In this case, we are employing this stopping strategy because if we find out that the HTTP service has terminated, we will stop the application. So how does the HTTP service now look like? And as shown on the slides, what is done here is the call of bind and handle with a route, and the route is defined up there in the companion object, like shown before. Get from resource directory and also get from resource for the root path, and that's all. So let's run it and show that it's really working. I'm glad that the Scala compiler is so slow, so I have time to drink. Okay, it's up and running. There's an info output here, which comes from the successful completion of the bind future. This guy here, bind and handle sends a server binding if it was successful. Okay, so we should now be able to delete or close this guy here and go to the localhost 9001 again and get the static template served by Akka HTTP. Hooray! So it's still a static template, but it's no longer open from the file system, but via the browser. Via the server. And of course, what we can do now, we can, let me just copy and paste. We can now send the delete to the root path, and that should shut down the server, and hooray, it has shut down. So this basic stuff seems to work. All right, any questions? I don't expect you to really understand it in depth, but hopefully get an idea and understanding of it. Okay, so then let's move on. Where's my slides? That slide should come later. No, anyway. So what we are going to do now here is take a look at the architecture of reactive flows in the first step on the single node. So the browser connects to the HTTP service via whatever get post or get for SSE. And there could be a post to create a new flow, or there could be a post to add a message, right? That is handled by the HTTP servers and then delegated to, let's say, the business logic. That's another actor. It's called flow facade. And that will, for example, send and add message to a flow, which is another actor. It's a particular actor for each flow. As you have seen before, there were flows like Akka, AngularJS. You can define them, and then you can send messages via this add message via the flow facade. So let's take a quick look at how this looks in code. So this is then the complete HTTP service. I think HTTP service now has become much more interesting than before. If you look at the route method here, let me scroll it up for you. You have more than just the assets and the shutdown. What you have now is quite a bit of code. You have the flows in addition. So here you have a path prefix of flows. So that means this will only match a request if it starts with flows. And then you have another path, a matcher, which extracts a segment that would then be the flow ID, right, or the flow name, and then a subpath of messages. That would be to get, here's the get, to get the messages for that particular flow, all the messages for, let's say, the Akka flow. And to get those messages, we go to the flow facade, we send the get message, and we ask for it. So we get back a future, and the future can be used to complete the request. There are two possibilities. If it is an unknown flow, we get status code not found. If we really receive back some messages, we send them back to the browser. And the question is, okay, how can we send, this is like a sequence of message, if you can read that. So that's a Scala object, right? How can we send that via HTTP? Yes?
Is this some kind of the get? It's like in play when we have async actors? Async actions.
It is sort of, but it's different. It's a little bit like that, it's a little bit like that. But under the hood, it's very different.
It's the same like non-blocking.
Sorry?
It's the same like non-blocking.
Yes. Very good. So the question is, how can we complete a request and send it via HTTP if it's a Scala object? Well, there needs to be some marshalling. It needs to be marshaled to whatever format we want to use, and of course we want to use JSON. So, and there's a whole JSON machinery which gets imported here via implicit conversion. Implicit conversions get imported, JSON protocol, spray JSON marshalling, all that stuff. That just makes it seamless. Don't want to really dive into the details here. And then there's other ways. So you can post a new message, again, to the flow. So we are still here in that block, right? So we can post a message. That's a HTTP verb again. And do a similar handling. Go to the flow facade, tell it to add messages. And what you also can do is you can just delete a flow, or you can get all the flows, or you can post a new flow. Okay? I think this DSL, so this is really a route DSL, it's pretty descriptive. And comparing with play, it's just Scala code. Okay, so it gets compiled. It's also more flexible. But I think an internal DSL as compared to an external DSL is the main difference between Akka HTTP and play in this place. All right, so the flow facade hasn't been shown to you. So let's do a quick look. Yes, of course.
Describe the flow of this message, how it goes through HTTP Akka and how it goes into the other actors and how it comes back to the response.
All right. Kann der auch pointen?
And how goes this in asynchronous way? That's synchronous.
Yeah, okay. The question was, how do the messages flow? So here's a couple of components which are important here. So first, browser sends a HTTP request. So the former spray IO has been incorporated in Akka 2.2 as Akka IO. It's non-blocking IO based on actors. Okay, it's using Java NIO from actors. So the first thing you get is like a TCP connection here. Essentially, you get some actor messages, some TCP actors. It's all low-level stuff already implemented. You don't have to care about that. But if you look at this HTTP object, which I have shown you before, where you invoke the bind and handle method, that does all that stuff for you. So you get essentially the HTTP requests become messages, okay? And they eventually will end up in your bind and handle method, okay? All asynchronous message passing between a couple of worker actors. A worker for the connection, maybe a worker for the request. It all depends on the implementation details. But there's a couple of actors sending messages to each other. And then finally, your bind and handle thingy, or not the bind and handle, sorry, the route, which is described here just as a DSL, that gets materialized. That's just a DSL. It gets materialized into actors. Okay. So again, actors are involved, and what will happen is that the message here in the HTTP service route triggers a message to the flow facade. Okay, that was explicit in the user code, which could be seen here. Like in this case, get messages. So you send a message to the flow facade. Okay. And message sending is always asynchronous in Akka. There's no way to block. There's no way to do a blocking message. Even if you do the ask pattern, it will give you a future, right? So that happens asynchronously. So the get messages, or in this case, the add flow is sent to the flow facade, or let's say the add message here, goes to the flow facade. The flow facade will check, oh, does the flow exist? And if yes, sends add message to the flow. Okay, and then the flow will, which is not shown here, forward back here to the HTTP service, flow added. Okay, sorry, message added, and the HTTP service will respond with a HTTP response to the browser. Does that make sense?
So the flow actor has a reference of HTTP service actor to send
It has no direct reference, but we're using forwarding here. Okay, so because the flow facade no, sorry, we're not using forwarding here. We're just using a future, and on success, so on completion of the future, we get back the message. So the HTTP service actor is the sender in this case, right? This actor is the sender, and the flow facade is asked, will respond to the sender, and then we have the sequence of messages, or we have the unknown flow response. And then we can go back to the browser by doing the complete. Yes.
Actually, you can use the form inside the facade. So you don't know who answered the message to the HTTP service, right?
Can you repeat the beginning?
I mean, you asked the flow
Yes.
facade,
Mm-hmm.
but the flow facade can forward the message to another actor, and this other actor can answer.
Sure, it could do that. Yeah, yeah. So you could also use a forward here to transparent to make it like opaque for the flow facade. Who was the sender? It's all possible. But I think in this case we want to have this cycle, which is not shown here. So an arrow is missing, and it goes back there. By the way, the code is up on GitHub, so you can dive into the details later if you want to. I think I'd better move on a little bit. So what we have now, let's just run that thing, is already sort of complete HTTP service. Let's create. Okay, I've created 2 flows, and it's not shown here. If I reload, it's shown. Like back in the old days, huh? It's already something. It's not really reactive. It doesn't react to these events, but okay, we'll get there. And you can do hello. Oh, let's reload. Yes. Okay, it's not reactive at all because it's like this complete HTTP service without the events, without the server-side push. And we need to get there. That's next. Server sent events. Who has heard about that? Okay, that's not too bad. Almost half. You could say it's WebSockets Lite. It's a standard. It's a standard which is very well supported by most browsers. It has been released as an official recommendation early this year. And it's a simple one-way channel to send messages from the server to the browser. And there's pros and cons if you compare it with web services. So, of course, if you need a two-way channel, two-way connection, you've got to use web services because server-sent events is just to push from the server. But if that's all you need, like in this case, it's much simpler because it's pure HTTP. There's no upgrading and all these complicated corner cases. And there's a lot of nice logic built into the JavaScript part of the SSE. It's called the event source. It does reconnect and stuff like that. So it's really convenient and easy to use. So if a single channel from the server to the client is enough for you, then I would go for server-sent events instead of WebSockets. So essentially, it looks like this. You just send a GET request, a normal GET request, and then the server will respond with a particular response. It has this media type, text event stream, and it is not closed. So the response is not closed. So the server just keeps it open, and whenever it wants to send a new event, it does it. If for some reason the connection goes down, the client will reconnect. And that's pretty sophisticated. It does that with an exponential backoff and stuff like that. So events are very simple. They are just a text format. The most important thing is the data fields. You can have multiple data fields. You can have an event field. You can also have a ID field for the last event ID, which I'm not using yet because the library I'm using here doesn't yet support it. But as I'm the author of that library, it will soon support it, which then could be used to really bring reactive flows to 100% event sourcing, maybe even CQRS. But I have to wait for your talk to really fully understand how to build that. Yeah, that's the most important parts here. So it's pretty simple, just HTTP. You can curl for it and just look at it. In the client, so let's go back to AngularJS JavaScript. You just use the event source object, which is available if you're not an Internet Explorer. You pass along a URI or just a path, whatever. You can also pass along a couple of properties. And then you register listeners. And in this case here, we register a listener for the edit event type. So here we have the event type. If there's no event type given in such an SSE, the default is message. But we are interested in edit and removed and these events. And then we need a function to handle the event. That's all you need to do in the browser. That's all you need to do. Compare or contrast that with WebSockets. Okay, and on the server, there's also almost nothing you have to do thanks to this library, Akka SSE, it is called. You just have some path, like here, message events, and then you have a GET request to that path. You complete it with an event source. Okay, that's a particular type of that library, which I will show you in detail in a couple of minutes. The architecture now becomes a little more involved. I hope you still recognize this part. If we want to add SSE, we need a couple of things, back channels, so to say. Let's look at one case. Let's look at this case here. If you want to add a flow, which I just did before using curl, and which did not result in the browser being updated. If you add a flow, the flow facade will not only send a message here to the flow, but it will also send a flow edit to a new actor, which is called mediator. That's essentially a pub sub thingy. So you can publish messages there to various channels, and others can register as listeners or subscribers. And we will have a subscriber that's called the flow event publisher. So whenever a flow edit message goes to this flow event publisher, that will create an SSE event. Okay? And that SSE event via so-called flow event source, that's just some API stuff, gets marshaled and properly formatted and goes back to the browser. Does that make sense from a high-level perspective? All right, so let's then see it in action. Couple of changes here. In addition to the route, which looked like this before, we have flow events and message events. These are given here. That's not a big deal. All we need to do is we need to create the respective event sources. Okay. So for each browser, we create a source which will send the events to the browser, to the client. And that's it. So how do we do that? for example, here, create event source. It's really simple. Just a couple of lines of code. Essentially, we use the Scala Stream API. The Scala Stream API is like a twin or a companion of the Akka HTTP API. It's a little more low-level and more generic. So there are sources and sinks and publishers and subscribers and stuff like that. So all we do is we create another actor. In this case here is the event flow event publisher actor. That's a simple actor, just a couple lines of code. One thing that's important is we subscribe ourselves, this actor here, to the mediator, which is passed in, okay? And then, whenever we receive a flow event, we call the onEvent method that will just send it downstreams. That's all you need to do. So let's run it. Up and running. So once again, let's create something, and hooray, it's there. And one more, it's there. And hello. Hooray. Okay, it seems to work. We could fire up second browser, do the same here. And yeah, it's all there. So now we really have a fully reactive, not yet resilient and elastic, but reacting to events-based web app. So, question is, what's next? How does our schedule look like? Okay, so if I go until 8, or maybe 5 minutes longer, and you start at 8:15. Okay. So, we have a single node app. That's certainly not resilient and not scalable. So we need a couple of more utilities to really become responsive and resilient and reactive. Okay? So the first thing I want to show you are conflict-free replicated data types. The question they answer are, how can we replicate data across multiple nodes in a cluster without central coordination? Central coordination is costly, okay? A single point of bottleneck, single point of failure. How can we avoid that? It has been proven not that long ago that certain data structures allow for eventual consistency without central coordination. There are two kinds of these. It's called state-based and operation-based. The state-based ones are the ones that are supported by Akka. They are convergent replicated data types. CV RDT is convergent. And they need a merge function. Think of a set. A set is a perfect example for that. A set, let's say a set where you can only add stuff. That's a really simple set, okay? If you replicate that and then send update messages to the replicas, it doesn't matter if you get those messages twice or 3 times, okay? So you can have a gossip protocol that just gossips the updates around, because it's idempotent to add an element to a set, right? So an add-only set is perfect CV RDT. And you can deal with removing elements from a set by having 2 sets, one for adding stuff and one for removing stuff. Clever trick. And Akka data replication offers a couple of other types like counter sets, maps, and some more. So whenever your type is one of those, you don't need central coordination, you can replicate your data. And by the way, replication is of course a way to build a resilient system, right? You need to replicate your data, because if one of the nodes crashes, it will lose all its data. probably. So how does Akka data replication work? You have a special actor on each node that participates in data replication. It's the replicator. It's an API, Akka API. And they communicate with each other via a gossip protocol. Gossiping means just random message sends. It's not completely random, but yeah, you can configure it a little bit. So your code, the user code, will send an update on one node. It will change the data, and the changes get disseminated through the cluster. And what you can do on another node, or in the same node, you can get. Or you can also register for changes, and then you will get changed messages. And that will be employed now in the next step here. I will fire up 2 nodes now. The second node, oops. Okay, this is the wrong directory. Oh, okay, I changed my iTerm settings. I need to go to project, and then I need to go to cd vector flows. Okay, now I can do it. Okay, now the second node listens on 9002. Okay, so let's again create. And now, as you can see here, we're only talking to node 1, 9001, right? So we create an Akka flow there, AngularJS flow there. Now we connect to 9002. It's not yet there. It's not yet there. That's bad.
I think you forgot to grow.
I forgot to grow. Are you sure?
Pretty much sure.
Thank you. You know, grow. I love you. That's great. Okay, I haven't moved on to the next, data replication. Thank you. Step in the sample solutions. I wouldn't have found that myself. Who was that? I owe you a beer. Well, it's free. Yeah. Okay, so let me just try it again. So here we go. And great, here we go. So not on 2, it's just there. Okay, it has been disseminated. The architecture here, you can look at the details later, is a little weird. I just wanted to show you data replication. So what we are doing here is not super resilient because we are just keeping the flows in memory, okay? So as long as there's always a node up, it will not lose any information about which flows are in the system. But once you shut down all the nodes, well, it's just a memory. It's sort of weird. It's not too weird because I know that some companies do stuff like that because they know they won't ever shut down all the nodes. But it's a rather rare occasion, I would say. Let me just briefly show you what's going on here, really briefly. So if you want to add a new flow, for example, what happens is after checking some stuff here, that's a really interesting part. We have the replicator actor, where we send a certain message. It's called replicator update. That's just a function. And it takes the existing map, because it's a map with flow names and flow info values, and adds this new key value pair. Okay, that's all what's going on here. That's really what has changed compared to what was there before. All right. So that was data replication, really awesome technology. We are also using it heavily in our current, in the product I'm currently working on at TypeSafe. And it has proven very, very helpful. And by the way, Conductor, our cluster-based application manager, is one of those where we don't store anything, because once you shut down all the Conductor instances, you have shut down all your applications you want to run with it. So it really doesn't make sense to persist anything. Okay. But on the other hand, if you have a cluster, make sure that one node is up all the time, maybe via multiple data centers. It won't lose any state thanks to data replication. Next thing is actor sharding. So sharding, in a nutshell, is just partitioning a large number, potentially large number of something across nodes in the cluster. It's known from databases, for example, but you can also use it in Akka. You can shard actors across multiple nodes. For example, one machine like this can usually hold 1 million or 10 million of empty actors. But what if your actors have lots of state, like the flows? They can contain thousands of messages, right? Then you probably want to just have multiple nodes holding your actors. To use Akka sharding, your actors must be addressable, must be addressable via an identifier. You must be able to talk to those via a name or an ID. This is possible here. Each flow will be sharded, and they have a name that is unique. So actor sharding will manage subsets of your actors. So they are grouped into shards, let's say into 10 or 20, and just moved in those shards across the cluster, and it dynamically adapts to the cluster topology, which means if you start with a single node, it will work. Then you fire up a second node, make it a member of the cluster, and eventually sharding will move a couple of shards over there. There's reallocation strategies you can configure, but it will react. And of course, if it detects that a node went down, it will then recreate those shards on existing nodes. So again, how does it work? Well, if you want to talk to an actor which is sharded, and we call these actors entities, they can be identified by an ID, we need to talk to them via the shard region actor. The shard region actor is an API from cluster sharding. Because we no longer know where the actor is, we don't have an actor ref. It is managed, it's created by sharding. So we talk to the shard region, we use the ID, the name, and the shard region knows where those guys live. So this shard region knows that A and B are living here, locally to it, whereas it knows that C is living over there, so it will then forward to its sibling shard region, and that one will talk to C. There's a little bit of central coordination, but just a little bit, whenever the topology changes. But sooner or later, those shard regions, the local shard regions, build all the knowledge in a decentralized way to be able to do the whole routing. Okie doke. So let's see that in action. I'm not forgetting G-roll this time. Firing up 2 nodes again. By default, sharding uses the, what is it called? Least allocation strategy. Well, if you want, we will create two flows, right? And one will be deployed on the first node, and the next will then be deployed on the second node by this default algorithm, okay? Least allocation strategy, I think that's the name for it. Okay, so let's do the same thing again. Let's create an Akka, AngularJS here. Oops, sorry. All right, here we go. Akka message send AngularJS. If we send 2 messages, we should now be able to see those here on this node too. Hooray, hooray. It works like expected. Now what happens if we bring down one of those nodes? For example, the second node. Just terminate it. If you go back here, yeah, Akka. Have you seen that? I clicked on AngularJS and it shows me Akka. Well, that's a, I would say, bug in the implementation here in the JavaScript, because if you now look at, where is it, error console? Ah, here. Okay, so we got back a 500. And that was because the other node went down. And it takes a little while for cluster sharding to recognize that, okay? And only then it will create the flow on the first node. So it looks like the Akka flow was created on the first node, which is still up and running, so therefore it still worked. But the AngularJS flow was created on the second node, that went down, and therefore when we wanted to go to that flow, we received our 500. Now, we no longer receive 500. So there was a certain delay, probably 3 or 5 seconds. That can be configured. There's a couple of configuration settings, and you shouldn't be too eager in declaring something dead. But yeah, that's always a little trade-off. There's one problem missing. Now, AngularJS flow is alive, but what's the problem here? We lost the message. And that's hopefully obvious, because if you look at this diagram again, let's assume this here was AngularJS, the AngularJS flow here. So once you shut down that system, that actor goes away. And it is then recreated by the shard region here as a fresh actor instance. It's just a different actor. It has the same ID, but it doesn't have any messages. So how do we deal with that? That's the last topic, persistence. The question is, how can we persist actor state, if that's necessary, to enable recovery of actors, recreating actors. And the only sane way is to use event sourcing, okay? And actually actors really fit very well. They receive messages and their internal state can only be changed by sending messages. So it's completely determined by the messages they receive. There's no other way. You can't just invoke a method on an actor to never get the reference to the actor. So, Akka persistence has a journal, and if you send a message, which is then in this terminology called command, you can validate it like add flow. If you say, yeah, really, I want to add the flow or add the message, the flow might not be valid to be added because it might already exist or something like that. Okay, then we create an event, and that is persisted by the journal first, okay? And only if the journal, which is essentially like, so there are a couple of journals out there. Usually you would use a journal database like LevelDB, but you can use anything from file or SQL database or in memory. You wrote a test driver, right? I'm using Mongo here because it's so super simple to set up. I wouldn't use it in production though. For this particular use case. So Kafka and Cassandra are probably the best options right now to do that. So yeah, once the journal says, okay, I have persisted that event, it goes back to the actor, and the actor then uses the event to change its state, okay? Only then. And on recovery, so whenever the actor is restarted or if it is recreated on a new node, on another node, like here in our example, those events are replayed, and you get the same state again. And of course, there's things like snapshots and ways to avoid waiting for that recovery for many, many minutes. So let me just show you that. IG row. I haven't yet shown you the flow. That was a normal actor before. And now it extends persistent actor. And a persistent actor has two methods, not just a receive, it has a receive command and a receive recover. And here, for example, get messages has nothing to do with persistence. You just respond with the messages. But you might want to create events which get persisted. Like here in this case, if you add a message, that's definitely something that needs to be persisted. So going here to that message, and then you invoke the persist method with an event you create, this message added event. Okay? And then you have to also provide a handler. So that's the guy here. And the handler is only invoked when the journal comes back with yes, I could persist that event. Okay, this guy has been persisted. No actor, you can use it to change your state or do whatever you want to do. And yeah, then we update the state, and then we just send around some messages. And in the case of recovery, only update state is called. So it's important to really distinguish between what affects the internal state of the actor and what are side effects, like sending messages to other actors, writing something into a SQL database. So you need to distinguish between those, because those side effects you don't want to repeat on recovery, usually. If they are idempotent, you could, but usually they are not. Okay, so that's the big change here. So let me just run that. Both are up. Okay, creating those two flows again. So flows are persistent, but not the flow names, the flow labels. So in order to show data replication. Okay, let's go here again. Akka 1, Akka 2, same here, 1 and 2. Okay, now we have our 4 messages. We are also able to see it here, right? Okay. There's also hello Akka, that's funny. Oh, that has also been persisted. Cool, no problem. I haven't cleaned my MongoDB anyway. So now I will kill that one. And as you can see here, you get this message that the address is gated unreachable. So it's detected unreachable, okay? And the configuration settings I have chosen will result in making, declaring that node down, dead, terminated after 1 second, okay? Usually 1 second is not a good value because unreachable could change into reachable again. Especially if you are like on Amazon, for example, there's more false positives or false unreachable than you would expect. So you gotta better tune your failure detector, which you can fine tune if you want to, and then not use an auto downing. Auto downing is dangerous anyway, so it's very good for demonstration purposes. So I'm back here, AngularJS, Akka. It just works, as you can see here. You may applaud now. All right, so as I said, the code is up on GitHub. If you're interested, take a look. You can also follow me. Thanks a lot, and